postdoc session with Bertrand Détoué. I remember it's 3 minutes. And please.
Okay, thank you. So I'm a postdoc working on particle physics, and more precisely my interests are related to studying quantum chromodynamics in high energy and high density limit, and in particular what we can learn from this domain by comparing what we can compute using perturbative techniques compared with what can be measured in experiments such as at the HC in high energy proton-proton and proton-nucleus collisions. So to give an example of what kind of processes we study, so the process that we studied recently, so at IPhT with Edmond and Gregory and also other people from other institutes, is the study of forward particle production at next to leading order in high energy proton-nucleus collisions. So this is quite simple process where we have a proton coming from the left which collides with a nucleus coming from the right, and the collinear quark from the proton will interact with the nucleus and go through multiple scatterings on the dense target, and so these multiple scatterings are resummed and they will give the quark a transverse kick, so then we can measure the transverse momentum of the ongoing quark. And so this process was studied at leading order already in the past. But as you can imagine, when you go to next to leading order, things become much more complicated. So in particular, we focused on the treatment of the running coupling in this part. So, thank you.
Thank you very much. And then we have Davide Napoletano, for which do you have a slide? No. For which we don't have a slide. So please, you want to try to put your microphone?
Hello? Okay, so sorry.
No. So actually we made it.
Okay. So I don't have a slide, mainly because of I'm protesting, I'm striking against the fact that only postdocs and students are here talking, whereas I was suggesting for also older people to give seminars and talk, so I was suggested to strike, and here I am doing that. This is why I don't have slides, though. What I'm doing is basically similar to what Bertrand was saying, i.e. my interest is in particle physics phenomenology in the context of high energy collision, proton-proton collisions, so what happens mainly at the LHC. And the idea is that you have two main goals, basically. One is to understand what happens during the collision of two protons, i.e. how the proton is made, basically, and the way is fundamental quarks interact within themselves. And the second part, which is what I'm working mainly on here, based in Clay, with Gregory, essentially, is how can you understand what happens, what are the product of this scattering. These are called mainly jets, because the products of the hard scattering are called jets. And by knowing, or rather by assuming how QCD works, you sort of try to guess how a jet would look like if it is from QCD, and then you look against data, and hopefully they are not what you expect, therefore something else has happened, and therefore you have this problem. I guess that's it.
Thank you very much. Perfect. So the next speaker will be Vincent Thiewis. I'm sorry if I don't pronouncing this right.
Yes, so my name is Vincent Thiewis. Don't mind the pronunciation. I've heard all variations of it. So I'm originally from the Netherlands, where I did my bachelor and master. For my master, I worked on radiative corrections to the dark matter relic density. But then I ventured more into LHC physics in my PhD in Münster. and which continued in a postdoc in Buffalo, New York. Now, officially, I am working currently in Göttingen, but through my funding through the DAD is I have an exchange service which allowed me to come here to France to the IPhT to work with Gregory Souillet on particle physics. And what I am currently looking at is using more modern techniques in jet physics to be able to say something about the precise measurement of the strong coupling constant. And specifically, I am looking at applying these techniques to older data, so E plus E minus collisions, where we might be able to offer some new insights into the old data. So, thank you very much.
Excellent, thank you very much. So the next is Ben Page. Please.
Hi, so my name's Ben. I've just arrived here in Paris about a week and a half ago. So I'm on the ANR grant of David Kosovo, Grisha Kochemsky, Pierre Vanov, and Benjamin Bassot. And I'm working in the amplitudes group. So my scientific career so far has essentially been working on new techniques and new ideas for increasing precision in the predictions made for colliders, for processes happening at colliders. And in the past few years, this has been a focus on new techniques for the calculation of scattering amplitudes in QCD. So specifically, this has been working to compute scattering amplitudes at two loops for higher multiplicity processes. So this is then relevant for us to be able to make next to leading order predictions at the LHC. So the new technique that I've been working on most recently is called numerical unitarity. This exploits the unitarity of the S matrix to help us evaluate a scattering amplitude numerically on a given kinematical point, which we can then plug into a cross-section calculation. So this started off with proof of concept, and since then we've applied this to pushing the multiplicity boundary in QCD, getting all the way up to two-loop five-parton amplitudes. Now these techniques involve a lot of technical detail, and they are essentially about taking a large integral and reducing it to a smaller set of integrals, using things like integration by parts identities, and more recently we've also been applying these to generic Feynman integral calculations. So that's me, thanks.
Thank you very much. And the next is Damalia Chakraborty.
Hi, I'm Dimpali Chakraborty. I'm originally from India and I'm a postdoc at IPhT. I'm here, or rather in IPhT, for the last 1.5 years. I'm working on theoretical condensed matter physics in the group of Catherine Pepin. So what we are working on is are materials which are based on copper oxide high temperature superconductors. They are commonly known as cuprates. They show a very rich phase diagram, and they show a lot of phases. They are a jungle of phases in this phase diagram. The parent material itself at half filling is an antiferromagnetic insulator, Mott insulator. Once it's whole doped, it shows D-wave superconductivity under a dome. It also shows charge-sensitive wave modulations in some parts of the phase diagram. Interestingly, at higher temperature, there is a mysterious pseudo-gap phase where the antinodal parts of the Brillouin zone are gapped out. Even 30 years after the discovery of these materials, there are many unsolved questions in this phase diagram. Specifically, this high temperature phase, pseudo-gap phase is still a big mystery in the community. To understand this pseudo-gap phase, we work in a SU2 picture which was proposed by Catherine and co-workers 5 years back, where two electronic phases, superconductivity and charge-sensitive wave order, they compete with each other strongly. Not only that they compete with each other, they are also connected by an emergent SU2 symmetry. To understand this, they sit on two sides of a seesaw, and the fluctuations associated with this symmetry gives rise to the higher temperature pseudo-gap phase. And this theory of SU2 theory is successful in explaining many experimental features of this pseudo-gap phase. And I'm also working on understanding some features of this pseudo-gap phase using this theory. I would be happy to discuss with you further in IPhT or even here. Thank you.
Thank you very much. So we have now Sebastian Gold, which is another striker maybe, because there is no slide. There is slide. Sorry. It's fine, I mean. We like strikes. Please, yeah, you don't. So please go ahead.
Yes, good evening, my name is Sebastian. I'm a postdoc at Lenka, working on applying statistical physics to inference problems. And to give you an idea of what such an inference problem might look like, I invited you to look at this graph and imagine that every node or each of the nodes of this graph is one member of the IPhT. Okay, this was taken on a random date, so there's only 12 nodes. And when there's a connection between the two nodes, these two nodes have a connection. Okay, they might work together, and they might be friends. And you can see that there's kind of a community structure here. There's three groups where there's a lot of connections in between them, and there's very little connections going on between the groups. And so, how might such a graph come about? Well, you might have different communities, say statistical physicists, cosmologists, quantum people. They all interact very strongly with each other. This is the signal. This is what you want to recover. Okay, and then there might be some noise, and this is what, as a statistical physicist, I mean by having people from two different communities talk to each other. Okay, and so then the problem of recovering these communities becomes the problem of really inferring the signal, the communities, in this noisy measurement, right? When you have just this as data and it's not plotted in a nice way, but rather a bit scrambled, and you only have the connections between them. Okay, and statistical physics can give you two things here. It can give you really algorithms that you can use to solve this problem. But it can also give you some tools to analyze kind of the general landscape or the general features of problems like this. And the picture that emerges is quite general. And this image is I've stolen from Lenka, actually. I hope she doesn't notice. The picture that emerges is quite general in that there's three regimes in these problems. Okay, and you can think of these three regimes as really a function of how much noise there's in the data. So in this case, how much crosstalk is there between the communities. It might be very easy to find the communities when there's very little crosstalk, very little noise. It might be impossible if there's just too much crosstalk and really the connections have nothing to do with the communities at the institute. And there's this intermediate hard region that is quite interesting because it's possible to find the solution, but it will take you very long. Okay. And what we try to do is to understand really, the goal of our research is to really understand where these transitions are between these different phases. And I guess the goal for the retreat is to make this graph look very much like it's in the impossible phase. Thanks.
Okay, thank you very much. The next one is Haggai Landa.
Like that?
Yes.
Okay.
You know what?
you. Do I have a slide? So my name is Chagai. I'm from Israel. I did my PhD in Tel Aviv, and I did a postdoc at the IPhT-TV in Paris Sud, Saclay. And my story with IPhT starts with Gregoire Misquich, who was working or still working in IPhT, and then came Marco. We should find a better picture to put on the web. No one
Machine learning.
And then they started discussing, and at some point they said, hey, we both love non-equilibrium dynamics, let's write a project. And this is how I was born. And what I did mostly and continue to do is more or less atomic and optical systems, laser cooling, which is far from equilibrium, process, cold atoms, jet scatter with cold ions, periodically modulated systems that go by the hot name of Loquet, and some dynamical systems, which is where this project connects somehow. I just say a few words about the project that we're making. It's about spins on a lattice. They interact, let's say nearest neighbor interactions. At each point on the lattice there is a spin. It's a model for magnetism. We consider the most complicated situation that Marco and Gregoire could think of, which is that you have a local gap of each spin. It costs more energy to the up. There is a drive that tries to rotate the spins along a transverse direction, a different direction. There is a damping that wants to take all the spins down. And there is non-equilibrium dynamics in the system. And even if you look at the mean field level of the system, at the mean magnetization vector of all the spins, where does it point? It's a classical system, and then you can see that although it's being damped, there are eventually two possible mean field solutions, steady-state solutions of the system. And when I talk about steady-state solutions in the classical regime, if this is the unit magnetization sphere of where the spins start, then you see that there is bistability encoded in two colors. And this is, of course, a semi-classical concept that doesn't exist in the original model that we started with, which is quantum. And this is where we try to describe the dynamics of the system, a bit in classical terms like bistability, two color codes that encode the magnetization pointing in one or two stable directions, and to go beyond that into answering the question of what is actually going on in the fully quantum system. Thank you.
Thank you very much. Yes, Francesco Peronasci.
Hello?
Please.
Hi. Okay, hi, I'm Francesco. So I'm from Italy, where I studied in Rome and Trieste. And at IPhT, I've been working for the last 2 years with Olivier and Marco. So I'm leaving in January to Germany. So I'm interested in general in strongly correlated systems. So these are systems in which, because of intraparticle interaction, you have many different phases. So for example, here the very well-known metal to multi-insulating transition, which as a function of U, which is local interaction, and double B, which is the free particle bandwidth. Basically, you can go from green, which is a metal, you have some density of states at zero energy, then to yellow, which is still a metal but it's somehow correlated, then red, which is a bad metal, something which has some density of states at zero energy but it's completely incoherent, and then finally to blue, which is a multi-insulating state. So in particular, we are interested in some non-equilibrium dynamics in these systems. And recently we have studied this model with oscillating interaction, and we have seen some interesting facts. So basically, when you start from some metallic state, so here in red, you have that your system thermalizes after some time. So here you go from left to right. And basically, the red curve is the distribution of states. And here, the flat distribution means that the system thermalizes to some maximum entropy maximum entropy state. But on the other hand, when you are in this multi-insulating state, which has this strongly these strong correlations, you have this predeterminization, which is this interesting long-lived state of matter in which your distribution strongly depends on the frequency, and so you see that here, even at a very long time, you don't go to this thermal state. So that's it. I'm here, and so we can talk about it if you're interested.
Thank you very much. My next one is Valentina Ross.
No? Yes. Okay. So my name is Valentina Ross and I'm a postdoc in Group C. I'm at IPhT since November 2016 and I'm staying here for the next 10 days, more or less. And before that, I did my PhD also in Italy, in Trieste, in SISSA, where I worked on the statistical physics of disorder systems, which is also what I'm working on right now. So previously I worked more on quantum systems and in particular on ergodicity breaking due to the disorder and to a phenomenon that is known as Anderson localization and its many-body version, which is called many-body localization. And more recently I'm focusing more on classical systems and in particular I'm looking at statistical properties of the geometry or topology of landscapes which are defined in very high dimension and which are complex, so in the sense that they are wrapped like in the picture, and these are the type of landscapes which emerge, for instance, in glasses. And I'm doing this together with Giulio Biroli. And this second slide here is just a follow-up of what, Ruben said before, namely that there is this wiki page for postdocs or also for whoever might find it interesting, where there are a lot of practical information, and this is free to modify, so anybody can go there and add information that they think is useful, especially for newcomers that maybe don't speak French already, and so might find it useful to have a reference point to get some information on practical things. Okay, that's it. Thanks.
Thank you very much. If we find a bank that speaks English in Paris, I think we will be all thrilled. Next one is Stephen Thompson.
Can everyone hear me? Like that?
Far. Yeah.
Okay. Better?
Yeah.
Okay, awesome. Right. Yes, I'm Stephen. I am a postdoc here working with Marcus Gero. I've been here for 2 years and I will be here for 1 more year. So I'm one of the small number of condensed matter theorists actually in the Institute. Before I came here, I did my PhD at the University of St Andrews in the UK. I worked with Frank Kruger and Chris Hilly. In my PhD, I worked on disorder in equilibrium, disorder in quantum systems in equilibrium, let's say. So I worked on a bunch of different things. The figures here are just to give you a little bit of a flavour of what I did. The first figure there is a phase diagram of a model of a ferromagnet, essentially. So near ferromagnetic quantum critical points, quantum fluctuations can cause new phases, new behaviour. I showed that if you add disorder into this, it triggers a phase called a helical glass, a new form of magnetic phase that has since been seen in experiments. From there, I did some work on bosonic models, so we use renormalization group to study disorder in bosonic models. These are things that can be realized in, say, ultra-cold atomic gases or in certain types of insulated magnetic systems. There we showed the presence of a thing called replica symmetry breaking, and we showed it was pretty critical to the thermodynamics of these models. This was surprising to an awful lot of people, so then together with some experimenters at the Universities of Strathclyde and Oxford, I designed a type of experiment, up here in orange and blue, to use quantum gas microscopes to start probing some properties of these systems and get a little bit closer to measuring the properties that I had predicted. Since moving here, working with Marco, I've moved from equilibrium into non-equilibrium, and I've largely moved from analytical to numerical work. So with Marco, we've been looking mostly at non-equilibrium effects in disordered quantum systems. Particularly, the big thing we've done so far was developing a method called flow equations to look at many-body localization. In this, we showed the presence of exponentially decaying local intervals of motion here in red and black. We have a method that maps the microscopic model into a phenomenological model. It's essentially a continuous unitary transform written in the language of RG. It allows us to reach much larger system sizes and a lot of other methods. And so far we've had some success in reproducing MBL phenomenology and dealing with the dynamics of MBL after quenches, and also looking into many-body localization in dimensions larger than 1. I think ours was the first work showing numerical evidence for MBL in 2D. We're currently tying up some work on quantum quenches in isolated spin glass systems. So for the statistical physicists, we're looking at the p-spin model. And for the people out there who deal with higher energy physics, we're currently looking into non-equilibrium dynamics of the Sachs-Levi-Kitaev model. I'm coming at this from a kinetic matter point of view, not a high energy point of view. So I don't know the high energy side very well, and I would appreciate anyone who has any input on that. So yeah, keywords basically disorder in non-equilibrium quantum systems. Thank you.
Okay. I believe it's Antoine Baker. Please, Antoine.
Yes, hi everyone. So my name is Antoine. So during my PhD, I was studying the DNA replication program, especially its dynamics. And for that, I was using model coming from statistical physics. And then I worked for a few years as a data scientist, applying machine learning to various kinds of problems. And now I'm working in the group of Lenka. So in the team, we are all interested in the statistical mechanics of machine learning. So let's say, for instance, that you have a task like tell apart if a picture is a cat or a dog. And then you may want to ask, is it even possible? How much data do I need? And is there a practical algorithm to achieve that task? And what we see, especially in high-dimensional systems, is that you have the presence of statistical thresholds. So, for instance, below some thresholds, you cannot do any better than random guess. Above some threshold, you can even achieve, on the opposite, perfect reconstruction. And there are some phases where you know theoretically that you could infer something, but you don't know any algorithm that can achieve this in a reasonable amount of time. So currently, more specifically, I'm looking at how structure in the data impact the learning procedure. So thank you.
Thank you very much. Let's move on with Bruno Blure.
Hi. Hi, I'm Bruno. I'm Brazilian. Before here, I was doing a PhD in Cambridge, so I put like some box about my interest, good memories of Cambridge. Back there, I was interested in something that was already mentioned here, which was holography, but different from Nick's talk, for example. I took more of a bottom-up approach, and I was interested in questions like if holography is any good to describe like strongly coupled theories that underlie condensed matter systems, for example, then we need to understand how to break the symmetries that are usually included in holography in GR. So in particular, we need to understand how to introduce disorder, which underlies many of the interest phenomenology in condensed matter. So I was basically trying to look at disorder in these theories that come from holography. All this terminology from disorder got me interested in the business. So I started also working in the, studying a bit of anomalous localization, like quantum phenomenology of disorder. Got interested in the SYK model from the high energy perspective. Worked a bit on that. And different, from many times in physics where we want to quantize our disorder, I kind of said, okay, I want to dequantize my disorder. So I applied for a postdoc with Lenka in IPhT, where I got interested in disorder systems from the classical statistical physics perspective. And more specifically, as was introduced by Sebastian and Antoine very well, in problems in the statistics where you have big data sets, and somehow you can map this inference and statistical learning problems into some kind of a statistical mechanics problem with a Gibbs measure, and somehow the thermodynamic limit is this big data limit. And then you get all the physics of glasses that appear, especially related to this hard phase already described by Antoine and by Sebastian. So I also wanted to put a picture of spin glasses there, keyword related, and then but Google doesn't know how to differentiate spinning glasses from spin glasses, so that's what I have for you. Thanks.
Thank you very much. Thank you. And then we can proceed with Heli Sarkar.
Hi everyone, I'm Saheli Sarkar. I'm a postdoctoral researcher here since this October with Catherine Pepa, and that is I joined just 2 weeks back. And I'll be working on copper oxide-based superconductivity and scaurians. I did my PhD from University of Illinois in Chicago. I was working